Hello and welcome, ladies and gentlemen, to the second webinar of the series about the new GOM software version V8 SR1. My name is Dinko Sabo and I have Stefan Siebold next to me for the question and answer section. So if you have any questions, use the Q&A section and Stefan will answer them. This webinar will be recorded so you can view the content again or share it with other people in your organization. We will show you how and where you can watch this webinar again, and also where you will find additional information at the end of the webinar. The topics for today are new functions and enhancements in GD&T. First, we will show you the linear size function to determine the sizes of elements. Then we'll show you how to check several elements together for positions using TED pattern. With projected tolerance zones, you can now offset tolerance zones. Unilateral tolerance zones on surface profile and line profile allow now to have asymmetric tolerance zones. We will show you how to create surface profiles on primitives, and we will introduce the new function symmetry on lines. We're going to talk about common datums and situation features, and finally, maximum material requirement and least material requirement on datums. Let us start with linear sizes. The applications where linear sizes are usually used are fitting applications and on determinations of the biggest and smallest sizes on areas of the inspected parts. The ISO 14405-1 includes the definition of the linear size operators. Linear sizes are available on features of size types, cylinder or circle, as well as two parallel opposite planes or lines. Linear sizes are able to explain dimensions, distances, much more detailed than a normal two-point dimension. The local two-point size is the default parameter when clicking on INspect linear size. It also represents, under certain circumstances, the independency principle. The independency and the envelope principle are still available as functions inside of the GD&T menu of INspect. Also Gaussian, maximum inscribed, minimum circumscribed, and Chebyshev checks are available. Diameters can be determined via the circumference, the area, the volume, and the spherical size. Rank orders are often used together with linear sizes. They are used for local size calculations on the actual data. The following rank orders are supported: maximum and minimum, average, median, mid-range, and range of sizes. The inspection values will be calculated based on section creation perpendicular to an element axis. Let me also add some additional explanations about rank orders. The median size will be calculated by arranging all the local sizes from the smallest value to the biggest value and picking the middle one. For example, if you have a list of values from 1.1 to 1.5, the median is 1.3. The mid-range size is maximum size minus minimum size divided by 2. The range will be calculated by maximum size minus minimum size. What you see here is a result of a linear size check. This check can be realized by selecting the element that you want to check and selecting linear size from the GD&T menu of INspect. The current visible check is an independency principle check, which can now also be performed by a linear size check. Nevertheless, the independency and the envelope principle are still available as functions inside of INspect to not break old workflows. When I now edit the creation parameters, you can see in the lower area the functions that were introduced for linear size. the computation method from 2-point size to size from sphere, and also the rank order drop-down field, which covers the range of possible rank orders from maximum size to range of sizes. The same applies for the lower limit. Usually the section direction will be calculated according to standards. If you need to define your own section direction, you can select user-defined from the drop-down menu. At the right side, you can now select the element which should define the direction. Let me show you some other usage possibilities. For example, the envelope requirement. When you switch on the envelope requirement, the software disables all other options and carries out all necessary steps automatically. It visualizes the cylinder that was calculated and shows you the inspected values. You can, for example, also use the Gaussian best fit to determine the maximum and minimum sizes of this cylinder. For doing this, just enable ACS, which stands for any cross-section, and switch the rank orders to maximum and minimum size. The software then will visualize where it found the maximum and minimum values and visualizes these positions with circles. When you select size from sphere, the software will help you to understand what actually happens on calculation. Therefore, it will visualize two spheres to show you where the maximum and minimum size has been calculated. Actually, it will show you where the spheres and with the resulting diameters will get stuck. As linear sizes are also available on parallel planes, I will also show you an example with two parallel planes. Out of those planes, I created a symmetry plane, which is checked with linear sizes. The green points that you see here are the creation points of this symmetry plane. Those elements can be visualized inside of the properties of the actual symmetry plane. When I again edit the creation parameters, you can see the available options for these planes. The linear size dialog is able to handle over 200 different inspections. The next function I want to show you is the TED pattern. The applications where TED patterns are usually used are pattern applications like on brake discs and plugs, where the positions of the holes are checked together as one element to determine if the part will fit to its counterpart. A TED pattern is used when checking several geometries together to determine if they meet the needed requirements. If all holes act simultaneously or with equal chance of contact, then they should be used as a pattern. For this inspection, I want to use a datum system. This datum system includes the plane A and the holes B and C. This datum system can be constructed by construct, local coordinate system, create datum system. The first datum will be selected by Control and left click. An additional method to select elements is simply to start typing its name. The software will then filter the list of available elements and only display the ones that are necessary in this case. The next step is to create an element group out of those elements. This can be carried out with selecting the elements, inspection, and create element group. This element group can now be checked by GD&T and TED pattern. Select the previously created datum system, set the corresponding type of tolerance zone, create the element, and close the dialog. The next new feature is the projected tolerance zone. The projected tolerance is a modifier used for threaded and press fit holes in order to ensure the proper fitments of the mating parts by means of pins or bolts. You have a plate with a hole in which a pin will be inserted. The projected portion of the pin will secure another mating plate. With projected tolerance zones, you are now able to determine the deviations not only limited to the actual data. In a lot of cases, you don't even have the actual data for the needed definition of the tolerance zone. For example, the part that has to be mounted is manufactured by a different company. I want to show you now an application example for a projected tolerance. But before, I want to explain a bit what a projected tolerance zone is. What you see here is the lower part of an assembly. This part has to be connected to the upper part with a pin. The area you are interested in is the red area of this part. The information that can be taken from the check is, will the pin fit or not? Now back to the training object. For carrying out a position check with a projected tolerance zone, you have to select the cylinders you want to inspect. Then select I inspect, GD&T, and position. Select the datum system if available. Select the type of tolerance zone and use the correct directions. In addition, you have to enable the projected tolerance zone. A projected tolerance zone needs a reference plane. In our case, this is the plane A. The distance and the length that you can enter here are taken from the values on the drawing. The software visualizes now the inspection values and also the tolerance zone and the result of the actual data. If you want to have more information, you can show the color deviation representation. Unilateral tolerance zones are also included now in our software. The applications where unilateral or bilateral tolerance zones are available for are surface profiles and line profiles. Unilateral tolerance zone means that the tolerance zone is moved in normal direction or against it. Equal or unequal distribution of the tolerance zone is possible. ISO and SME notations are available and are visible inside the inspection labels. Let me explain a bit more about the differences in calculations. On the first picture, you see a classical tolerance zone evenly distributed around the cut surface. The second picture shows you a bilateral tolerance zone which is shifted out of the part. If the drawing mentions a value of 0 for the tolerance zone, which you can see in picture 4, this value means that the upper tolerance limit is represented directly by the cut surface, and the rest of the tolerance zone is shifted into the part. With higher values than 0, the tolerance zone is shifted more and more out of the part. The ISO standard calculates it a bit different. ISO moves the center of the tolerance zone by the corresponding value, which is visible inside of the feature control frame. I prepared a project with a patch compound on which the surface profile with unilateral tolerance zone has to be checked. Just select the surface profile and select the option Surface Profile from the GD&T menu of iInspect. Set the datum system if available and enable the usage of the unequally disposed tolerance zone. Available methods are the ISO standard and the SME standard. The software will also visualize inside of the label which standard was used. In case of the ISO standard, these are the letters U, Z. In case of the SME standard, this is the letter U. A very nice and easy to use function is the surface profile on primitives. The profile of a surface can be used for advanced freeform surfaces, such as when a surface curves in multiple axes at once. Commonly, casted parts use the surface profile when the surface is curved to control the amount of variation. For checking the surface profile of primitives, additional patch compounds are no longer needed. The inspection is now directly available at the element. For a surface profile check on primitives, simply select the elements that you want to check. And apply the surface profile check directly without any usage of patch compounds. Again, select the datum system, and now it's even possible to use unequally disposed tolerance zones for this, again with the ISO and SME standard. We also introduced the possibility to check the symmetry of lines. Symmetry is a condition in which a feature or features are symmetrically disposed about the center line or center plane of another feature. The center line or plane of the second feature is usually specified as a datum. The software now offers the check of the symmetry of lines against datum systems or against other symmetric lines. In this example, I want to check the symmetry of the inner area of the M in regards to the outer areas. I already created a report page which includes a section, the needed lines and symmetry lines. The symmetry line B, which has to be checked against the symmetry line A. The symmetry line A results from line A1 and A2, and the symmetry line B, which results from B1 and B2. To perform the check, select the element, open inspect, select symmetry, select its datum system, in our case it's now symmetry line datum A, and close the dialog and apply the check. The software department also added advanced possibilities for the usage of common datums and situation features. Common datums are necessary when you want to combine several elements to only one datum. Those areas are often used for mounting points to additional parts of an assembly. Situation features are used when not all constraints should be used for the element. You are now also able to select which constraints should be blocked by using the modifiers plane PL, straight line SL, or point PT. We improved the dialog for datum systems and added situation features to this dialog. This dialog empowers you to combine several elements to a datum and is not limited to a datum combination of only 2 elements. Inside this project, I included a drawing which shows you a common datum system for the datum A. The datum A is based on circular planes A1 to A5 with a diameter of 5 mm. Let us now switch to the inspection workspace. I already constructed the planes A1 to A4. Let me now show you how to create the plane A5 with a circular selection. Click on Construct, Plane, and Fitting Plane. And in addition, go to Edit, Selection in 3D, Geometry-based selections, select by geometry contour. Select the needed geometry, in our case this is the circle 5, and apply the needed selection distance. Apply the selection and close the dialog. And create the plane and close the dialog again. In addition, we also need the measuring principle reference construction. Let's now create the datum system by construct local coordinate system, create datum system. In advanced, I selected all planes by selecting the category planes. Just click inside to the drop-down menu and click on Insert Currently Selected Elements. This will add all selected elements as a common datum. And now it's even no problem if the planes are located on different heights. I'll start right away with the creation of the datum system by clicking on Construct, Create Datum System, add the selected elements, and the software will start with the calculation of the datum system. If you need different settings than the default ones, you can disable certain degrees of freedom by deactivating, for example, SL, which stands for straight line. As you can see, the software now visualizes only one plane. The remaining degrees of freedom are only 2 translations and 1 rotation, in contrast to the previous settings. When I deactivate plane and activate straight line, the software will show you which constraints now will be used. As you can see now, only a line will be used as a datum, and therefore only 1 translation and 1 rotation is not restricted. Let us come to the maximum material requirement on datums. If you want to ensure that 2 parts never interfere or limit the amount of interference between the parts when they are at their worst tolerances, MMR can be called out. Take a shaft that must go through a hole with clearance between the two. The MMR of the shaft would be the maximum diameter. The MMR of the hole would be its minimum diameter. If you made sure that the MMR of the shaft was always smaller than the MMR of the hole, you guarantee there will always be clearance between the parts. This is important for any tolerance tag to ensure that when the tolerances are at their least desirable condition, the part still functions properly. Now you can add maximum and least material requirements also on datums to fulfill growing part and drawing demands. As we want to use the maximum or least material requirement on inspections, we have to apply the independency principle to those elements. This applies to the inspection elements as well as to elements used for a datum system. To carry out the independency principle, I'll just select the cylinders that will be used and apply the independency principle. For better visibility, I will switch off the cylinders and choose the visualization name. Now it's time to construct the datum system. Select the datums A, B, and C, and in addition enable the usage of the maximum material requirement. To carry out the check, I'll select the cylinders 1 to 4 and select head pattern from the GD&T menu of inspect. Select the created datum system, the correct type of tolerance zone, and activate the usage of the maximum material requirements. Set the needed tolerance from the drawing. And create and close the check. The software now visualizes what the maximum material requirement stands for. It is a check if the part is true to gauge and will fit to its counterpart. We have almost reached the end of the webinar. There are also additional information we would like to mention. You can download a beta version of the V8 SR1 already. GOM has launched the Open Beta program in order to give you the opportunity to try out new functions and enhancements without affecting your daily business. The V8 SR1 will run with the current V8 license, so there is no need to update your license. Please find more information and the software packages under the following path: support.gom.com, download software, overview, GOM software V8 SR1. The final release is planned in mid-January 2016. As mentioned at the beginning, this webinar was recorded. You will find the video for download in the support area and also on the GOM Metrology YouTube channel. In addition, we have produced video tutorials for the new functions, which are also available on YouTube and in the GOM service area for download. You can find a detailed list of new features in the direct help. We also implemented the links to the video tutorials for the new functions. The next webinar in our series about the new version V8 SR1 is the virtual measuring room and will take place on December the 10th. This was the webinar GD&T. We will stay online for a while to answer your questions in the Q&A section. Thank you very much for your attention. We hope you enjoyed it. Have a nice day and auf Wiedersehen.